Hello students, this is Indrani ma'am from SIP Rasayan. In this lecture, I will explain some exceptions on ionization enthalpy. Now see, these are elements of period 2. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. So we know from left to right in the periodic table, with increasing atomic number, atomic size decreases. As we know, ionization enthalpy is inversely proportional to atomic size. So left to right, here ionization enthalpy should increase. It should be like that. But two exceptions are here. Beryllium is having higher ionization enthalpy than boron. So here is one exception, and nitrogen is having higher ionization enthalpy than oxygen. So here one exception is there. So what's the reason for that exception? Now see, beryllium is having atomic number 4, 1s2, 2s2 is its electronic configuration. And boron is having atomic number 5, it is having electronic configuration 1s2, 2s2, 2p1. So here S subshell is fully filled, but here P subshell is not fully filled. We know full filled and half filled subshells are exceptionally stable. So it's very difficult to remove one electron from this beryllium. This is one reason. In another way, you can think penetration power of S subshell is more than P. So it's very difficult to remove one electron from S subshell than from P subshell. So if it's difficult to remove this electron than this, obviously beryllium will have higher ionization enthalpy. Now what's the reason for higher ionization enthalpy of nitrogen than oxygen? We have to think about its electronic configuration first. Now see, atomic number of nitrogen is 7, oxygen is 8. This is electronic configuration of nitrogen, this is electronic configuration of oxygen. So we see here, total capacity of P subshell is 6. Here 3 electrons are there in the P subshell. So it is half filled. So half filled subshells are exceptionally stable. Therefore it's very difficult to remove one electron from here than from here. So obviously it is having higher ionization enthalpy than oxygen. Now see, these are elements of period 3 in the periodic table. Now see here, with increasing atomic number from left to right, atomic size decreases, so ionization enthalpy should increase. It should be like that. But two exceptions are here also, here and here. Magnesium is having higher ionization enthalpy than aluminium, and phosphorus is having higher ionization enthalpy than sulfur. Magnesium is having atomic number 12 and aluminium is having atomic number 13. Now consider the electronic configuration of magnesium and aluminium. Now see, these are the electronic configuration of magnesium and aluminium. You can see here 1s2, 2s2, 2p6, 3s2. So here electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p1. So whatever explanation I gave here, by same explanation you can explain this thing also. Similarly, atomic number of phosphorus and sulfur are 15 and 16 respectively, and these are electronic configurations. So here it is half filled, exceptionally stable. So it's difficult to remove electron from that subshell, as I told you in this case. So for the same reason, it is having higher ionization enthalpy than this. Now we will see next exception. We know as we go down the group in the periodic table, there is increase in the number of shell. So electrons can easily be removed. Therefore ionization enthalpy decreases as we go down the group. Now if you consider group 13 elements, boron, aluminium, gallium, indium, thallium. It is in period 2, it is in 3, it is in 4, this is 5, this is 6. So down the group ionization enthalpy should decrease. Therefore, expected order is this one. But here observed value for aluminium is almost similar to gallium, and thallium is having higher ionization enthalpy than indium. So why it is like that? Gallium is having atomic number 31, it is having this electronic configuration. So it is having d orbitals electrons, and you know screening power of the subshell decreases in this direction. So d subshell is having less screening effect. That means these electrons are having less screening power. So there is attraction between nucleus and valence shell electrons. So it's difficult to remove those electrons. And here no d electrons. So what will happen? These values of ionization enthalpy will be almost similar. Aluminium is having 577.4 kilojoule per mole, and gallium is having 579.0 kilojoule per mole. Now thallium is having atomic number 81. So there will be lanthanoid contraction, and due to lanthanoid contraction it is having F subshell electrons which are having very less screening power. So it's very difficult to remove those electrons. That's why thallium is having higher ionization enthalpy value than indium. Another exception is there in group 14. Elements are carbon, silicon, germanium, tin, lead. So down the group what will happen? This value should decrease. But if you observe, lead is having higher ionization enthalpy than tin. Lead is having atomic number 82. So here also due to lanthanoid contraction, it's very difficult to remove one electron from valence shell. Therefore, ionization enthalpy is higher than tin. This video is till this. If you like, please subscribe. Thank you for watching.